Determining the wattage of a stereo system at different frequencies, such as 60 Hz, when you only know the wattage at 100 Hz, is not a straightforward calculation. The power output of an amplifier is significantly influenced by its design, the impedance of the speakers, and the frequency of the audio signal. Without detailed specifications, it's nearly impossible to accurately extrapolate the wattage at one frequency from the wattage at another. Let's explore the factors that make this calculation so complex. Firstly, the amplifier's frequency response plays a critical role. An amplifier's frequency response is a measure of its ability to reproduce audio signals at different frequencies accurately. An ideal amplifier would have a flat frequency response, meaning it amplifies all frequencies equally. However, real-world amplifiers have limitations and their frequency response may vary. Some amplifiers might be designed to boost certain frequencies while attenuating others. This is often done intentionally to compensate for the characteristics of the speakers or to achieve a specific sound signature. If an amplifier's frequency response is not flat, the wattage output will differ at different frequencies. For example, if the amplifier is designed to provide more power at 100 Hz than at 60 Hz, the wattage at 60 Hz will be lower than the specified 320 watts at 100 Hz. Secondly, the impedance of the speakers is another crucial factor. Speakers have an impedance rating, typically measured in ohms, which represents the resistance they offer to the flow of electrical current. The impedance of a speaker is not constant across all frequencies. It varies depending on the design of the speaker and the frequency of the audio signal. At certain frequencies, the impedance might be higher, while at others it might be lower. This variation in impedance affects the amount of power the amplifier can deliver to the speaker. The power delivered to the speaker is calculated using the formula power equals voltage squared divided by impedance. This formula shows that the power delivered is inversely proportional to the impedance. Therefore, if the impedance of the speaker is higher at 60 Hz than at 100 Hz, the power delivered at 60 Hz will be lower, even if the amplifier is producing the same voltage. Thirdly, the amplifier's design and components significantly influence its performance at different frequencies. Amplifiers use various components such as transistors, capacitors, and inductors, each of which has its own frequency-dependent characteristics. These components affect the amplifier's ability to amplify signals at different frequencies. For example, capacitors have impedance that decreases with increasing frequency, while inductors have impedance that increases with increasing frequency. These frequency-dependent impedances can alter the amplifier's gain and output power at different frequencies. An amplifier designed for high-fidelity audio reproduction will typically use high-quality components and a sophisticated circuit designed to minimize these frequency-dependent effects. However, even in high-end amplifiers, some variation in performance across the audio spectrum is inevitable. Fourthly, the power supply of the amplifier is another factor to consider. The power supply provides the electrical energy needed for the amplifier to function. If the power supply is not robust enough to deliver sufficient current at all frequencies, the amplifier's output power may be limited, especially at lower frequencies. Lower frequencies require more energy to reproduce because they involve larger current excursions and higher current demands from the amplifier. A weak power supply might struggle to deliver this current, resulting in a decrease in wattage output at 60 Hz compared to 100 Hz. Fifthly, harmonic distortion can affect the perceived wattage at different frequencies. Harmonic distortion occurs when the amplifier introduces unwanted harmonics, which are multiples of the original signal frequency. These harmonics can alter the sound of the audio signal and affect the perceived power output. Some amplifiers might produce more harmonic distortion at certain frequencies than at others. If the amplifier produces more harmonic distortion at 60 Hz than at 100 Hz, the perceived wattage at 60 Hz might be lower, even if the actual power output is similar. Sixthly, the speaker enclosure and its design play a role. The speaker enclosure is designed to optimize the speaker's performance by controlling the way sound waves are radiated. The enclosure's design affects the speaker's frequency response and impedance characteristics. A well-designed enclosure can improve the speaker's efficiency at certain frequencies, while a poorly designed enclosure can degrade performance. If the speaker enclosure is not optimized for 60 Hz, the speaker's output at the frequency might be lower, resulting in a lower perceived wattage. Seventhly, the room acoustics can affect the perceived sound level at different frequencies. The room in which the stereo system is placed has its own acoustic characteristics, which can influence the way sound waves propagate. Some rooms might have resonant frequencies that amplify certain frequencies while attenuating others. If the room has a resonant frequency near 60 Hz, the sound level at that frequency might be higher, while if the room attenuates 60 Hz, the sound level might be lower. These room acoustics can affect the perceived wattage of the stereo system at different frequencies. Eighthly, compression and limiting circuits in the amplifier might affect the wattage at different frequencies. Compression and limiting circuits are designed to prevent the amplifier from clipping, which occurs when the amplifier attempts to produce a signal that exceeds its maximum voltage or current capabilities. Clipping can cause distortion and damage to the speakers. Compression circuits reduce the dynamic range of the audio signal, while limiting circuits prevent the signal from exceeding a certain level. These circuits might be frequency dependent, meaning they affect certain frequencies more than others. If the compression or limiting circuits are more active at 60 Hz than at 100 Hz, the wattage at 60 Hz might be lower. Ninthly, thermal considerations can limit the wattage output. Amplifiers generate heat as they operate, and excessive heat can damage the amplifier's components. To prevent overheating, amplifiers often include thermal protection circuits that reduce the output power when the amplifier reaches a certain temperature. The amount of heat generated by the amplifier depends on the power output and the efficiency of the amplifier. If the amplifier is less efficient at 60 Hz than at 100 Hz, it will generate more heat at 60 Hz, which might trigger the thermal protection circuits and reduce the wattage output. Tenthly, the type of music or audio content being played can affect the perceived wattage. Different types of music have different frequency content. Some genres of music, such as bass-heavy electronic music, contain more energy at lower frequencies, while other genres, such as classical music, contain more energy at higher frequencies. If the music being played has more energy at 100 Hz than at 60 Hz, the perceived wattage at 100 Hz might be higher. Given these complexities, accurately determining the wattage at 60 Hz without additional information is extremely difficult. To estimate the wattage at 60 Hz, one would need to know the amplifier's frequency response, the speaker's impedance curve, the amplifier's design characteristics, and the characteristics of the power supply. If this information is available, it might be possible to create a rough estimate of the wattage at 60 Hz. However, without this information, any attempt to calculate the wattage would be speculative. In conclusion, while the specifications state 320 watts at 100 Hz, there are numerous factors that influence how the amplifier performs at 60 Hz. To truly understand the power output at different frequencies, detailed measurements and specifications are required. Without these, it's best not to assume a linear relationship between wattage and frequency.